Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to address the question, when do fractional differential equations have maximal solutions? Now, this video is part of a forthcoming research paper of mine to appear in the journal Fractional Differential Calculus, and I'll post a link in the description when it's ready. Anyway, I hope you enjoy it. I hope you find it useful. Now, I'm going to present two results today. One is a comparison theorem, and the other one is this existence theorem for these maximal and minimal solutions. Now, the level of this particular video is for anybody who knows a little bit about differential equations. Say you might have done a Calc 3 course and say a second course in differential equations. It uses mainly sequential techniques. Now, even if you don't have that background, just have a look anyway and see if you like it. Let me share my screen with you and we can get underway. When do fractional differential equations have maximal solutions? Well, I'm glad you asked. Now, before we get down to business, first of all, a few preliminaries. R is going to denote this two-dimensional rectangle. So if I was to draw a little rectangle, say in the TU plane, let's just say draw it here. That might be your big A. The width of, or the height of the rectangle is 2b, 2 big B, and this little end part would be little b. By the way, if you're watching on a mobile, could you let me know what the font is like? I'm trying to get better with my mobile ready presentations. Okay, so this then is this rectangle. That's going to turn out to be the domain of a function in our differential equation. Now, here is the problem that we are going to look at. Now, dq is the fractional differential operator. F is a function that is defined on this set and is continuous. A is just some number, which turns out to be this A up here. And you'll see this is a little bit different from the regular differential equations you might see, because you've got this x naught in here. And this left-hand side is known as a Caputo derivative, okay? Okay, so that equation one, the initial value problem for these fractional differential equations, is going to be our main area of investigation. Now, you might think, well, what use is a fractional differential equation or a fractional derivative? The q in equation one can be between 0 and 1, a half, for example. Now, fractional derivatives and fractional differential calculus have been around for hundreds of years, dating back to the 1600s. Now, it does have important applications in so-called fractional diffusion in applied mathematics, but the nature of this presentation is relatively pure. Okay, so this is our main problem. F could be non-linear here, by the way. Now, this is the way we define the fractional derivative of order q between 0 and 1 of some function y. Okay, you'll notice that we've got just the regular derivative and an integral here. Okay, so before we press on, let's talk about what we mean by a solution to a fractional differential equation. And loosely speaking, it's just a function that satisfies problem one, okay? All right, so let's define what we mean by a solution. Well, a solution is, in this case, say a function of t, and there's some interval where zeros are part of the interval I. This left-hand side is defined, well defined, for every t in that interval I. The domain, x is in the domain of f, so basically the right-hand side's defined. The two sides are equal and the initial condition is satisfied. Okay? So when we look for solutions to these kinds of problems, the challenge is to find or produce an interval I and a function x where all these things are satisfied. Okay? Now that definition may seem crazy, it's very convoluted, but essentially you're just looking for an interval and a function where they satisfy problem 1. Okay, so what is a maximal solution? What do we mean when we say a maximal solution, and why is it important? Now, in reference number 2, and I'll show you this at the end, the authors gave sufficient continuity conditions involving f under which so-called maximal and minimal solutions to problem 1 would exist. Now, they had this kind of interval. Now, B is from the rectangle. Here, gamma is the famous gamma function. N's a positive constant to be defined a little later. Okay, it turns out that this big N is just the bound of f on this rectangle. But it's well known, for example, in my papers and many others, that the optimal interval for the existence of a solution to problem 1 is of this form. Now, this, if you compare this with this, you'll see that this is actually a larger interval than that. Okay? So when I was reading paper reference number 2, I was thinking, hang on, this interval looks a little bit weird. So let's look at this a bit more. And I thought, hang on, well, why doesn't their interval line up with best practice in this existence theory intervals? So that's what I decided to look into, and that's how the results came about. Now, what do we mean by maximal solution? Let me share with you. All right, suppose that I have, let's just move that up a bit. All right, so what I'm trying to do is align best practice in the literature. All right, so let's say I have a point A here, and here's 0, and here's one solution to problem 1, here's another solution, and here's another solution. Now, this top solution is called a maximal solution to 1 if all the other possible solutions to the problem stay below that curve. Okay, and similarly, you can talk about a minimal solution if you have another function, say down here, that satisfies problem 1, and all the other solutions to problem 1 stay above that graph. Okay, all right. So I thought, okay, let's improve this interval and bring it into line with this interval for maximal and minimal solutions. Okay. So we're now at a point where I can share the first result with you. It's called a comparison result. Okay, and we're going to use it in the main part of the main result. Okay, here it is, a comparison theorem. Now what we're doing is basically just comparing two solutions. All right, so let W be defined on the same rectangle as before, and it satisfies some sort of inequality known as a Lipschitz condition. This is a very famous condition in the area of differential equations. Okay, so for all pairs of points in the rectangle, we have this kind of inequality for some positive constant r. Now, let x be a function that satisfies this kind of problem. Now, note there's an inequality there, not an equality on some interval. Let y be another function that satisfies the same kind of problem, but not with inequality, with equality. So there you've got a differential equation and an initial condition. Now, if you look at the two initial conditions and big A is less than or equal to alpha, then it's claimed that the solution to this problem stays below the solution to this problem. So let me just sort of draw a little picture there to make it a little bit more clear. Okay, so let's say you've got alpha here and A there. Y would look like that and X might look like that. Okay, that's all it's saying geometrically. All right, and this is sort of framed within some, I don't know, some sort of bigger rectangle or something like that. Okay. So that's the first preliminary result. Now, I'm not claiming that comparison theorem is strictly mine, okay? It's a basic result. It may be in the literature somewhere else. I couldn't find it exactly, but it may be out there. And this is not the focus of this particular presentation. I'll show you the main result in a minute that relies on this comparison theorem. Okay, so how do we prove it? Well, basically, you prove it by assuming that this isn't true, and you end up with some sort of nonsense. Okay, so let's assume this is the case, and X looks like that, and Y looks like that. Okay, so there is a point, say T1, where X is greater than Y at T1. And there'll be also, by continuity, there'll be a point T0 where they touch. Okay, now this kind of scenario is going to lead us to some sort of nonsense. So let's check it out. All right. So here's the proof. So assume that there is a point, T1, so T1 there, such that the conclusion isn't true. Okay, so that X of T1 is greater than T1. And to simplify notation, let's define R of T to be the difference, X minus Y. Okay, from this point, we know that R of 0, because this is less than or equal to 0, is less than or equal to 0, and R of T1 is positive. Okay. Now, let T0 denote the greatest value in this interval such that R of T0 equals 0. So in this picture, that's this point here where they cross. Now, for all T in this interval, we have this curve the X curve lying above the Y curve, okay, on this interval, with R of T strictly greater than 0 on this sort of left open interval, okay? Now, let's compute a derivative there. We know what R of T is. Let's compute this fractional derivative, or this Caputo derivative. Now, R of T0 0, remember, so this isn't going to make much of a difference. Okay, so if you write that down and look at the difference, you get the following. Now, remember, X is a solution to this problem by assumption. Y is a solution to this problem. So what I can do is I can replace this with an inequality and put in WTX. Now I can replace this with equality and get this. And I just keep the inequality there. Okay? And what is this? Well, I know by assumption, by assumption 3, that W satisfies a Lipschitz condition. Okay? Now we don't have the absolute values there because R is greater than or equal to 0, so you don't need the absolute values there. Anyway, that is using 3, and we can just write that in terms of R. It's L of R of T. So now I have another differential inequality involving this R, the difference of X and Y. Okay, so we've now got this differential inequality. What can we do with it? Well, we're going to use something called Gronwall's inequality, and I have papers and videos on that, and I can put the link, say, in the description for that, or you can search my YouTube channel. So how does that work? All right, so we've produced, as I said, an initial value problem using an inequality, and it's a so-called linear fractional differential equation, differential inequality. This is satisfied on this kind of interval from T0 to T1. Okay, now this, using Gronow's inequality, you can recast this in this following integral form, again, keeping the inequality. And it follows from this so-called Gronow's inequality that every function that satisfies this integral inequality must be non-positive. Okay? It must be non-positive. But hang on. R of t is non-positive on this interval, but hang on, look at the picture. R is positive on this interval. So that means we've been led to some sort of contradiction, some sort of nonsense. How can R be non-positive and positive at the same time? It can't work. So what do we know? We look back and go, okay, well, something mustn't be right. So if we look back, we see that there is no point such that this happens. So what does that mean? It means that R's got to be less than or equal to 0, and that means X lies below Y. Okay? So that's your standard proof for that comparison theorem. Now let's move on to the main result. Okay? So this is the main result, the main contribution that the research paper and this video makes. Okay, here it is. Theorem 3. Suppose f is continuous on this rectangle that I defined at the start, and that we're considering this initial value problem. Okay, so this is the same as 1. All right. Now, I claim that if f is continuous, just continuous, then this fractional initial value problem has at least one solution, and in particular, there is a maximal solution on this interval where this is the same as 2. So this is so this interval and this interval is the same as 2. By the way, I've got an m here. The m and the m are different, okay? Now, the n here and the m here, I know it's a little bit confusing, but basically that is just a value where f is bounded by this m on the rectangle. F's continuous, so the bound always exists. Okay, so yeah, sorry, so the m and the m here don't have anything to do with each other. Okay. Okay, so again, what we're concluding there is the problem has a solution just under the assumption of continuity, and there's a maximal solution. There's a biggest solution, if you like. There's a solution whose curve stays above all the other solutions. Now, on the flip side, there's also a minimum solution that stays below all the other solutions to the problem. I'm not going to talk about that particular case. This video is going to be long enough without me talking about the minimum values or minimal values. All right, so that's the main result. Let's talk about the proof. So what we're going to do is use the idea of an approximation of polynomials. I am going to replace this problem with a sequence of problems where f is approximated by polynomials. Okay? And in particular, there is a theorem due to Carl Weierstrass, who's one of my heroes, that says, okay, if f's continuous on this rectangle, I can always find a sequence of polynomials in 2 dimensions where the sequence of polynomials converges uniformly on the rectangle to f. Now that's an amazing result. So we're actually going to look at how polynomials can shine the light on these nonlinear F problems. All right. Now, each polynomial is Lipschitz on R. Okay, I talked about a Lipschitz condition in the comparison theorem. And there's, for each n, there'll be a Lipschitz constant, L sub n. And because of the convergence, without loss of generality, we can assume that the sequence of polynomials stays above our f on the rectangle. We can also assume that m is a joint bound on both f and our polynomials on the rectangle. Okay, so now our interest moves a little bit to a sequence of problems where the right-hand side is no longer this f, but it's a sequence of approximative polynomials. Okay, and I've got this sequence here. Now, the right-hand side is Lipschitz for every n. So I know from one of my papers and others that for every n, this problem has a unique solution, x1, x2, x3, x4. Okay, so what we've done is we've taken our original problem, we've approximated the right-hand side through sequences of polynomials, and we've now made discovered some information about that approximative problem. For every n, the initial value problem has a solution. What we're going to do now is show that in that sequence of solutions to the polynomial problem can be related to the original problem. We're going to show that the sequence of solutions to the polynomial problem has a subsequence that converges to has a convergent limit whose limit satisfies the original problem. Okay, let's have a look at that. Okay, so this problem's got a unique solution for every n. So we're going to do two things. We're going to show that our sequence has a uniformly convergent subsequence by applying an idea called the Arzela Ascoli Theorem. And you can do that by showing the xn is uniformly bounded and equicontinuous. Okay, well, firstly, the uniform bound on this problem, on this sequence, follows from the fact that, okay, for every n, this graph has to stay in the rectangle. So, of course, it's going to be bounded. Now, secondly, the uniform equicontinuity is a little bit harder to show. I'm not going to show you all the details here because it takes quite a while, but I'll just put them up on the screen. Okay, it's quite long. So suppose I've got T1 and T2 are points. Let's look at the absolute value of the difference. What I want to do is make that small when T1 and T2 are small. Okay, so I can play with the integral representations a little bit, and I'll get down to here. And you can see that if T1 and T2 are close together, then this can be made as small as we like. And if you want, as a sort of independent exercise, try looking at the case T2 less than T1. Okay, so we conclude that our sequence of solutions to our polynomial, let me put that up there. We conclude that our sequence of solutions to our polynomial problem actually have a subsequence that converges. Okay, so we're going to apply the Arzela Ascoli theorem. There's going to be a subsequence that we know has a limit. All right, let's talk about that for a while. All right. Now, by the Arzela Ascoli theorem, there is a function, let's call it x sub m, where x sub m is a function of t. And this x sub m is a uniform limit of some subsequence. You don't know what the subsequence is, or don't know how to choose the subsequence, but the Arzela Ascoli Theorem says that there is a subsequence whose limit is this. Okay? All right. So the last thing we need to do now is to show that this limit function, x sub m, really does solve the original problem, and then what does it look like geometrically compared with all the other solutions? All right, so it's pretty easy to show that the above limit function really does satisfy the original initial value problem with the f. Okay, so basically let's look at this difference here. Now, this, if I bracket off that, that is just basically the a's will cancel, and this can go, if you expand this, you'll get this. Now, because these approximate, because P sub nk converges uniformly to F, this difference can be made as small as we like. And this is what this represents. So let's take the limit. This will go off to 0, right? So I've got the absolute value is less than 0. What happens? Well, everything inside this absolute value has to be 0, right? And the limit, this will become x sub big M. This will become x sub big M. And what do we have then? Well, we get this. Okay, so we've taken the limits, we've replaced this with x sub m, this with x sub m, and I get this. So the absolute value is less than or equal to 0. So that means that this has to hold. So what does it mean? It means that this magical limit function satisfies our original problem 1. Whew. Okay. So the very last thing we need to do now is talk about the geometry, or where this x sub m sits. Is it really a maximal solution? And it is. Let's talk about that. All right. There is a continuous function such that this holds, and this x sub m is a solution to our original problem. Okay, what we want to do now is show that x sub m lies above all the other solutions to our original problem on this interval. So how do we do that? Well, what haven't we used yet? We haven't used the comparison theorem that I proved before this main theorem. So now it's the place where we're going to use this comparison theorem. All right, now I told you earlier that without loss of generality, that the sequence of approximative polynomials could be chosen so they lie above our f on the rectangle R. And so what does that mean? It means that I can set up a sequence of an initial value problem with an inequality, and one with an equality. Okay, so basically these are just, if I can just find it here, where is it? Okay, you'll see in this case we've got one with an inequality and one with an equality, right? So basically this is just mimicking 4 and 5 over here. And we know from the conclusion of theorem 2 that this has to happen. Now in the limit, of course, this goes to x sub m. So if x is any other solution to the problem, to the original problem, then x sub m has to lie above or on x. So we conclude that x sub m is a maximal solution. Now we're almost there. We're almost finished. The last question is x sub m the maximal solution? And it is, but I'm not going to tell you why. So if you have any comments, why is there one and only one maximal solution, and only one minimal solution, put them in the comment section. Now you can rearrange things here and come up with another theorem saying if f's continuous on this rectangle, then there's a minimal solution as well. But again, I'm going to leave that alone. Anyway, I hope you enjoyed this presentation. If you have any comments, any questions, put them in the comment section, and hope you enjoyed this this sharing of research. All right. Thanks again, everyone. Bye.